Welcome back, everyone. So in this video, we're going to tackle a subject that a lot of students struggle with, but that is hopefully going to be easier once we cover it and you think about how to work with it, and that is mechanisms and arrow pushing. So when we're looking at how reactions occur and we're trying to understand the potential energy surfaces so that we can predict the outcome of a future reaction, with a current reaction, we're looking at how electrons move from an electron-rich site to an electron-deficient site. And we do this by drawing out what we call an arrow pushing mechanism. And arrows are used to depict the flow of electrons, and they're really just an accounting tool. They're a way of bookkeeping to keep track of all of the atoms and electrons in our system. So before we get too far into this, really the questions that we are going to be asking are, where are the electrons? And where do they want to go? Right? So we'll get into this in more detail, but these are the two questions that at every step of every reaction you should be asking yourself. Where are the electrons in these substructures I just drew? And where do they want to go? Or what are the most electron deficient sites? So one of the ways that we can address this is by defining our substrates in terms of electron-rich and electron-poor systems. So we define these as nucleophiles, which are electron-rich, nucleus-loving, or direct translation. Those can be things like lone pairs, an example here. That could also just be a standard lone pair. Right? They can also be pi bonds. Or highly polarized sigma bonds between things like lithium and carbon. So the ones that we're going to most concern ourselves with in the remainder of this course are going to be the lone pairs and anions. So those are examples of nucleophiles. If you're going on to take the rest of 2220, you're going to be therefore concerned with these as well. So don't forget them. That's nucleophiles. These are where the electrons are. Right? The electrophiles are electron poor. Or electron-loving species. Right? So these include things like positive charges or polarized bonds. You can also see these carbonyls are a great example of this, right, where they have a resonance structure that has positive charge on the carbon. So these centers here are electron deficient. So if you have something electron rich, this is going to be the site that they choose to attack. All right, so now that we've defined kind of where the electrons are and where they want to be based on functionalities of molecules, let's talk about how we decide or draw arrows to indicate that they are moving between these sites or sharing electrons between nucleophiles and electrophiles. So arrows indicate movement of electrons. So remember, we've already seen these arrows before. Now we're going to focus primarily in this video on 2 electron processes. We'll talk about 1 electron when we get to radical chemistry. They don't necessarily follow all of the same rules of nucleophiles and electrophiles, but we'll get there. So before I get rid of that, remember that you are moving electrons, not atoms and not positive charges. So that means that arrows flow from your nucleophile to electrophile. Never the other way around. Nothing with a positive charge will ever have an arrow pointing away from it. All right, so an example of this would be this here. So this is carbonyl chemistry, something we're not going to see much of in this course, but let's just take this as a practice of electron flow. So we're given this, and we want to form that species, right? So that's 1 intermediate. The first question we have to ask, well, let's start with what bonds are we forming? We are forming a new carbon-oxygen bond, this one here, and we are breaking one of the carbon-oxygen-carbonyl bonds. So in order to do that, we have to identify what is our nucleophile and what is our electrophile. Well, our nucleophile has the negative charge. Our electrophile is this carbon here. We'll indicate it with an E. That's the most electron deficient center because it is polarized by the carbonyl oxygen. Right? So we can draw this by taking the lone pair, drawing an arrow to the carbon, which indicates that this lone pair here is being shared between that oxygen and this carbon. Now, if we stopped there, we would violate the octet rule because we've added an additional bond to carbon, but we haven't broken any of the bonds to that carbon. So we also have to break one of the pi bonds. And we break that one because that is the weakest bond. And it gets us to our product. So in one step, we have shown that we can take the electrons from our nucleophile, move them to our electrophile, and because we know the octet rule, we're not going to violate the octet rule, and we have to break that carbonyl bond. So that's an example of an arrow pushing mechanism, right? You always start from the electron-rich site. You always maintain that you need to account for the octet rule. Also notice that we started with a negative charge and we ended with a negative charge. So be sure to account for your charges. Right? Let's do another example. Um, we'll get into a lot of this later on, but let's say we have, so you'll see more of this chemistry later, but let's say we have this reaction, right? So let's take a look first at what's going on here. Well, we are clearly breaking a carbon-chlorine bond, right? And sometimes it helps to just write this somewhere on your page while you're doing this. Remember, this is just bookkeeping, so you can take notes wherever you want. Break carbon-chlorine. You're also going to end up making this oxygen-carbon bond. Remember, this here is our CH3 that is currently attached to our chlorine. So make CO bond. Okay, so one way you can do this is directly by having this come in. Now, if that comes in, right, we're taking those 2 electrons from that oxygen and we are sharing them with that carbon. That means that we have to kick that chlorine off. Right? So these are very simple mechanisms. We'll get into some of the details of other systems like this when we get into substitution elimination chemistry. But keep in mind that you are looking for the most electron deficient center, right? That's going to be the carbon that has the chlorine attached to it. And the electron rich site, which is, in this case, your oxygen. Okay? So common mistakes and things I don't ever want to see you do. Make sure you draw all arrows. Right? So if we have a base, and we are drawing a mechanism to show how this would deprotonate, if we draw just this, what we get out of that step is this here. Right? You've only shared electrons with the hydrogen. You haven't broken a single bond to that hydrogen. So this is bad. No. In order to fix that, what you want to do is break the bond between the carbon and the hydrogen, right? So now you're making the bond between the base and the hydrogen, and you're sharing the electrons from the carbon-hydrogen bond with just the carbon. Now remember that we also have to conserve charge, so here everything is neutral in the starting material. Therefore, if we're going to form a carbanion, that means that our base now becomes a cation. All right. Other things to watch out for. Remember, do not violate the octet rule. People often have problems with nitrogen in that way, right? Because nitrogen has a positive charge in an ammonia state, but that means that it does not have the same properties as a carbon with a positive charge. It doesn't have an empty p orbital. It has a full octet. It's sharing all of its electrons. So if you have something like a nucleophile, and we often indicate this as Nu, this cannot come in. what that would do is produce a nitrogen with 5 bonds. Yikes, right? So that cannot happen. Instead, remember that so if you have a nucleophile with ammonia, remember that this proton is acidic. So you could potentially and now we make sure we conserve our positive charge. So we've drawn an arrow from the nucleophile, or what would be a base, to the proton. We've broken the nitrogen-hydrogen bond to form ammonia and our protonated nucleophile. Okay? So hopefully that gives you some idea of the standard bookkeeping of mechanisms and electron flow. Please remember that really the key is these two things. Where are your electrons and where do they want to go? In multi-step reactions, if you just ask yourself that at every step of the way, you'll figure out the mechanism pretty readily, and you don't need to memorize anything in order to do it. Okay, I hope this helps. See you guys later.